Section 4.7, Dividing Polynomials. We're going to take this section in two parts, and in this first part, we're going to look only at divisors that are monomials. To divide any polynomial by a monomial, she gives us a rule here in the textbook toward the beginning of the section, page 311. And I want to look at this rule very closely because it should look familiar to you. This is our rule for adding fractions. It's just shown backwards. Here on the right hand side, if I have two fractions that have a common denominator, I can add them up by adding the numerators and writing that result over this common denominator. Another way to look at this, think about it like this. If I wanted to divide x plus 6 divided by 2, that's a single term in the bottom, my divisor is a monomial, isn't this the same as saying 1/2 times that binomial? Dividing by 2 and multiplying by 1/2 are the same thing. And if I look at it this way, I can distribute that 1/2 to get 1/2 times x, multiply the tops, multiply the bottoms. That'll give me x over 2 and plus 6 over 2, which I would write as 3 in a final answer. But look how my rule applies to this situation. I can take every term in this numerator, the x and the 6, and divide each and every term by that denominator, by that divisor. Divide every term by 2. Now, we've talked about this before in chapter 3, where we had to divide both sides of an equation to get it in slope-intercept form, and we said to divide both sides of the equation by a number is to divide each and every term by that number. And we explained it this way, saying that because it's the same as distributing a 1/2, I could consider this just distributing a divided by 2. Distribute that division to each term in that numerator. So either way you want to look at it. Look at it as distributing division, or think of it in terms of unadding a fraction. Either way, it boils down to this. And she says it in the blue box, page 311 at the top. To divide a polynomial by a monomial, divide each term of the polynomial by that monomial. So that's all there is to monomial divisors. This is the easy part. Here at the end, I'm going to comment on what we're up against next in the rest of 4.7. But let's focus on these monomial divisors. We're ready to grab some homework problems. I'm going to start with number 8. And here we have a trinomial divided by a monomial. We have a trinomial of degree 6 divided by a monomial of degree 1. And according to the rule, we can perform this division by dividing every term of that trinomial by this monomial. Now, right here, let's look at this. Right here, I could write minus, and then my term 60x cubed over 2x. There's nothing wrong with that. However, when it comes to monomial divisors, I prefer to see my sign remain with its original term. I'd like to keep that minus on the 60, and I will explain that here in a couple problems. I'm going to think of everything in terms of addition and keep signs with their original terms, and I'll show you how that's going to keep us out of trouble here down the road. And then finally, plus this third term over this common monomial divisor. Now simplify each term. 120 over 2 is 60. X to the 6th over x, how many are left and where? 5 x's in the numerator. Nothing remains in the denominator. That would be over 1. We don't write over 1. My middle term, negative 60 divided by positive 2 is going to be minus 30. X cubed over x leaves x squared. 2 factors of x in the top. Nothing left behind in that denominator. And plus 80 divided by 2 is 40. X squared over x leaves 1 factor of x in that numerator. And there it is. And these are easy to check. How do you check a division problem? You multiply. If I wanted to check this real fast, I would just say, what is 2x times this quotient? The quotient times the divisor should return the original dividend, that original numerator. And so this is a quick and easy check. Distribute that 2x, and we'll get 120 x to the 6th minus 60 x cubed and plus 80, and x times x is x squared. That matches my original dividend, this original numerator, and so that checks. Let's do another one. Let's grab number 14 now. A trinomial divided by a monomial. And the method we're using of distributing this division or splitting apart a fraction, however you wanted to think about that, works only when I have a monomial divisor. Next time we'll talk about what happens if there's a binomial in this denominator. And that gets messy. So for now, we know that to divide a polynomial by a monomial, we divide each term of the polynomial by that monomial. And now simplify each term. In this first term, these 5's, they're gone. They cross cancel completely as we reduce this fraction. T to the 8th over t leaves 7 factors of t in the numerator. Nothing's left in the denominator. Plus, these 5's cancel. T to the 7 over t leaves t to the 6th power. And plus. Now what's going on here? Well, I know that 5 goes into 15 3 times. That's all I can do to reduce that fraction. And what am I left with? A 3 in the top and a t in the bottom. And that's my answer. It actually turns out that this answer is not a polynomial. Do you remember your definition of polynomial? All of the terms would have to look like a, x to the n, where a is real, and what? N has to be a whole number. Well, what does this last term look like? 3t to the negative 1, doesn't it? If I shove that t back up in the top, if he crosses the fraction bar, that was t to the first in the bottom becomes t to the negative 1 when he's sitting up in the numerator with that 3. Negative 1 is not a whole number. And we said back in section 4.4 that one thing that would kick an expression out from being a polynomial is if I had variables in denominators. So you can divide two polynomials and the answer is not a polynomial. That's fine. We're still going to do it. Be sure you understand how this last term worked. All we had to do was simplify. All we had to do was reduce that fraction. All right. Let's try number 16. Now in number 16, we have a negative coefficient in our denominator. Now this is the reason I mentioned in our first problem that I like keeping signs with their terms when I work these types of problems. I'll show you how that's going to keep me out of trouble. Our rule says that to divide a polynomial by a monomial, we divide each term of that polynomial by this common monomial divisor. I like to do this all in terms of addition and keep this negative with that 8x. And right here is the reason. I am more likely to make a mistake. I mean, there is nothing wrong with writing minus, letting this minus stand for this guy. Nothing wrong with putting that minus there. But I'm going to get in a hurry reducing these fractions. It might slip my mind that I've got a negative divided by a negative, which is going to be positive. For that reason, I like to keep my negatives with their terms and do all the terms in terms of addition. That gets that negative right up in my face, and I am not nearly as likely to make a silly mistake of just simply seeing that negative in the numerator by having them sitting out front. Just a suggestion, but I strongly encourage you, when working problems of this type, keep negatives with their original terms and put this all in terms of addition. Now let's simplify each of these three terms. My first term, 32 divided by negative 8 is negative 4. X to the 8th over x squared leaves x to the 6th. 24 divided by negative 8 will give me minus 3. X to the 5th over x squared will leave 3 factors of x in that numerator. And on this last term, a negative divided by a negative is positive. 8 divided by 8 is 1. In other words, the 8's cancel. And what am I left with? X over x squared. 1x in the top, 2 in the bottom. Leaves me 1 factor of x in the bottom. This time I actually need to show a 1 since there was nothing left behind in that numerator to hold place. So it leaves behind that residual factor of 1, that multiplicative nothing. I like to keep signs with their original terms in these problems. I promise you that will make it much less likely that you make a silly sign error that will end up costing you points. Number 30. Now I'm not going to copy number 30 to the board. You have your book with you. And so we have this polynomial of 5 terms over a monomial divisor. To divide by a monomial, you divide every single term of that polynomial in the numerator by this common monomial divisor. So I'm going to start with the first step. I'm not going to copy the problem from the book. I'm going to go ahead and split this up. Start with my first step. Plus the second term over this monomial divisor, plus this third term over my monomial divisor, plus, here again, I'm going to keep this negative with the 7k as I write my fourth term over this monomial divisor, and finally plus this fifth term over that same divisor. So I've started with the first step. The original problem is there. This is number 30 there in the book. Now simplify each of these 5 terms. First term, negative over a negative is positive. 8 divided by 2 is 4. K to the 4th over k leaves k cubed. Next term, positive divided by a negative is negative. 12 over 2 is 6. K cubed over k leaves 2 factors of k in the numerator. Next term, positive divided by a negative is negative. The 2's will cancel. And k cubed over, did I miscopy? I did. Sorry guys, that should be a k squared right there. I miscopied that from the text. Let's start this term again. Positive divided by a negative is negative. The 2's cancel. K squared over k. All that leaves behind is a single factor of k in the numerator. Fourth term, a negative divided by a negative is positive. 7 divided by 2. You got that concept now? If I ask you, what is 7 divided by 2? What are you going to tell me? 7 halves, right? Because it doesn't divide out evenly. It doesn't reduce, so let's just leave 7 halves. And what happens here? K over k, those cancel. So there are no k's in this term. And my last term, don't make this harder than it needs to be. A positive divided by a negative is negative. What else can you do? There's nothing else you can do. That's already in lowest terms. So minus a 3 over 2k. Don't make that last term harder than it needs to be. You're just simplifying each of these 5 terms. So practically that means you're reducing every one of these fractions. We got down here to the end. A positive over a negative gives me minus, and the rest of it could not be reduced, so leave it alone. And that's my answer. Let's have a go at number 36. Now notice here in your book that number 36 is written with a division sign. Instead, I will copy this one just so we can point this out on the board. It's written with a division sign instead of a fraction bar. Well, that's fine. A fraction bar is what? A division sign as well as a grouping symbol. Our order of operations says that when you have a fraction bar, you do what's on top, you do what's on bottom, and finally the last thing that you do is perform the division indicated by the fraction bar. So that's all right here for us. The parentheses provide the grouping this time. My division sign provides the division. A fraction bar is just a division symbol with the power of grouping. The fraction bar is a division sign, which is also a grouping symbol. So that's all covered by my parentheses and my little division sign. We still work the problem the same way. Divide every term in my dividend, which would normally be my numerator if it were written with a fraction bar. divide every term in my dividend in this polynomial by this monomial divisor. So we will have this first term for my dividend over my common monomial divisor, and plus second term over this common divisor, plus, I like keeping negatives with their original terms in these problems, so let me put that minus 6y to the 5th over 3y to the 8th, and plus my fourth term over this same divisor. Just like we've done all the other problems. Now, what did we see in the last problem? All we're really doing in simplifying these four terms is basically reducing them, right? This first term, 45 divided by 3 leaves a 15 in the numerator. I mean, I could think of that as cross-canceling if I wanted. 3 goes into 45 15 times. I could look at it as cross-canceling. Y to the 7th over y to the 8th. How many are left and where? That's our quotient rule. And we like to say how many are left and where when I'm done canceling factors common to the top and bottom. If there's 7 in the top, 8 in the bottom, when I'm done canceling, that leaves me one factor of y in this denominator. And this term is simplified. There's nothing else I can do to it. Let's keep going. Plus, 9 divided by 3 leaves a 3 in the numerator. Y to the 6th over y to the 8th. How many are left and where? Two factors of y in the bottom. In my third term, a negative divided by a positive is negative. In my final answer, I do like to see this out in front as a subtraction sign. But in the steps of my problem, I really like to keep that negative with its term for these types of problems. Negative divided by a positive, we write minus. 6 divided by 3 leaves a 2 in the numerator. Y to the 5th over y to the 8th. How many are left and where? 3 factors of y in that denominator. And finally, plus 12 over 3 leaves a 4 in the numerator. Y to the 4th over y to the 8th leaves y to the 4th in that denominator. And there's my answer. Now I've got one that I want you to try. I want you to try this next one, and then we'll get back together after you pause and attempt it and compare answers. This is number 38, and I know some of you have your textbook on your laptop and it's not as convenient to go finding this homework problem in the text while you're watching a video. So let me go ahead and write this up here. Let me write a little smaller because I don't think I have enough room to copy it at the size I was doing. 200 a to the 5th b to the 6th minus 160 a to the 4th b to the 7th minus 120 a cubed b to the 9th plus 40 a squared b squared, all divided by 40 a squared b. So you go ahead and pause the video there, and when you're done, come back and we'll compare answers. In setting this problem up, just like all the rest, we have a monomial divisor. So all we have to do is distribute that division to each of these four terms, or think of it as she stated the rule. It looks like our rule for adding fractions backwards. I kind of like the idea of distributing this division. A lot of you are going to say, do I have to write this middle step? Because I think I can just do that in my head. No, you don't have to write the middle step. But if I don't have the shown work, then I don't have anything to go to for partial credit. So that's entirely up to you. I, of course, am going to show this step on the board for the sake of our notes. Notice once again, I am keeping the negative with its term. That's the habit I want to be in, especially when I run into a divisor that turns out to be negative. That is a wide problem, isn't it? I've divided now each term by that same monomial divisor. Now we simplify each of these four fraction terms. In my first term, 200 over 40. Well, that's the same as 20 over 4, and that's 5. When I look at the a's, I'm left with 3 factors of a in the top. I look at the b's. How many are left and where? 5 b's in the top. Nothing survives in the denominator. We don't write over 1. Next term. Negative divided by positive is negative, so I'll write minus. 160 over 40. Well, that's the same as 16 over 4, and that's 4. A to the 4th over a squared leaves a squared in the top. B to the 7 over b to the 1st. That's b to the 6th. Also in the numerator, nothing survived the denominator. A negative divided by a positive is negative. 120 over 40, well, that's the same as 12 over 4. So we've got a minus 3. What survives here? A single factor of a in the top and 8 factors of b in that numerator. Nothing's left behind in this denominator. And finally, plus, the 40s cancel, the a squareds cancel. The only thing that survives is 1 factor of b in that numerator. How'd you do? Now this is the easy part. This is the easy part of this section. I would encourage you to glance ahead, but I mean don't freak out, but just glance ahead. Here's our blue box that we've been using to work all of the problems in this first part of this section. You turn the page, she has a blue box that goes on for almost a page and a half, describing what we're going to be doing when we have divisors that are not single terms, divisors that are not monomials. And she's working one here for you in this giant blue box that has a binomial divisor. Now let me give you a warning. I will expect you to be familiar with long division of numbers. Okay? I'm not going to teach you how to divide numbers using long division. That's certainly something with which you should be familiar. If not, get that figured out before it's time to look at this second part of this section. Because it is the same idea that we use for long division of numbers that we're going to use as we look at long division of polynomials. So something to think about, but right now I want you to focus on monomial divisors. So this will take you up through homework problem number 37 for now. 7 to 37, the odd. I'll leave you to it, let you get started on that homework, and do be sure and at least glance ahead and make sure that you know everything there is to know about long division when it comes to just numbers, because we are going to apply those concepts to long division of polynomials.